Good morning, Mandara. Today I am here to explain about modeling and stability analysis of ESC, internal voltage in DC link voltage control time scale. So here, in the recent years, renewable energy resources sources including hydropower, onshore, offshore wind farms, and solar photovoltaic power plants have grown rapidly. These resources are widely used and represent a reliable, economical, and environmental friendly alternatives to the traditional means of electricity generation. In addition to other environmental goals, the European Union has set a target to expanding its share of renewable energy to 27% by 2030. Therefore, the trend to RES is constantly increasing in the future. The wind energy is widely regarded as a major source of large-scale renewable energy systems. In order to integrate these renewable energy resources in the utility grid, the electrical power transmission system is required to have a high degree of reliability and efficiency, but these requirements do not available in the AC transmission systems, which is also not feasible for transmission distances larger than 400 kilometers of AC overhead lines due to high reactive currents and undesirable wave reflections. High voltage High voltage direct current transmission (HVDC) is an efficient alternative to overcome these limitations. The HVDC system is regarded as the best choice for long distance power transmission that integrates RES in the public network and promotes the use of RES in cost-effective and efficient manner. In addition to by employing such modern technology, the interconnection between the countries can be established and the electricity market can be supported and completed. A classical technology of HVDC transmission system is implemented in line commutated converter based HVDC systems, which has been implemented using thyristor based converters. In 1972, the first project with the thyristor valves has been established as a back to 1972. The first project with the thyristor valves has been established. The LCC converter has been modified to other configurations. In some applications such as capacitor commutator converters, in which series capacitors are attached to the converters between valves and transformers. This configuration has been served as a section of the commutation voltage to enhance voltage stability and provide some of the converter reactive power compensation. Another configuration is called controlled series capacitor converter. HVDC technology has a transition from conventional thyristor-based HVDC that suffers from the commutation failure and thyristor valves of voltage source converter-based HVDC VSC HVDC due to the development of power electronics technologies. In 1994, a small-scale HVDC system with two VSCs based on IGBTs has been put into operation. VSC HVDC makes the use of pulse width modulation techniques easy. Such techniques enable the generation of modulated technology signals with a predefined voltage amplitude and quite instantaneously away from the AC system. VSC-based HVDC system depends worthy and growing technology for remote integration of RES due to its key features. In contrast to its traditional LCC-based HVDC counterpart, these benefits include black start capability, management of active and reactive power independently, and power reversal capability without the need to change the polarity of DC voltage. In addition, a connection can be established with weak AC grids and passive networks. One of the key factors that contributes to the grid weaknesses is the high impedance characterization due to the remotely located RES. Such factor increases the challenges of stability and optimal operation of the power networks. Therefore, the control and operation of converters connected to the grid are seen to be a striking research direction. The understudy HVDC system The understudy the HVDC system consists of three-level neutral point clamped NPC. connected as a back-to-back connection through DC link capable depending on vector current control technique. The VSC analysis and control are controlled by operating the system and DQ axis, which permits an independent active reactive power control. The VSC control permits regulating the DC link voltage VDC and maintaining it in order to keep the balance between the DC link power and AC power. PWM PSC connected to the AC grid. Here we can see the diagram. AC grid connected to converter reactor, rectifier connected to rectifier, capacitance, DC cable, inverter, converter reactor and AC grid filter. So in the second diagram, you can see VA, VB, VC are connected to resistance and inductance and connected to VA, VB, VC. There is a current flowing which is IDC, IC and IL, capacitor and in inductor. According to the equation, by applying standard Kirchhoff's voltage law, VABC is equals to R into IABC plus L into D by dt IABC plus VABC, where the measured three-phase voltages and current of the AC grid are defined as VABC, IABC, converter input voltages R and L depend the filter resistance and inductance respectively between the AC grid and VSC and the VSC. According to the converter, three-phase voltages and currents are converted into constant vectors in the steady state with synchronous rotating speed at a specific fundamental frequency. L into di by dt is equals to minus R I into d plus W L IQ minus VD plus VD. So the relationship between the input IC and output DC powers can be expressed P is equals to 3 by 2 of VDID plus VQ into dot IQ VDIDC. IDC is equals to C into VDC by DT plus IL. So the Q axis component of the grid voltage is defined as VQ is equals to 0 due to the alignment of its D axis component along the D axis direction through the instantaneous real and reactive power. P is equals to 3 by T VD. Q is equals to 3 by 2 VD into IQ. Therefore, by employing the transformation into rotating DQ coordinate, the active component of current which supplies the essential power feed to the DC bus and reactive components of current are utilized. The three-phase VSC is controlled by two control loops, inner current control loop and outer voltage control loop. In such control, the inner current control loop exhibits a faster response compared to that obtained from the outer DC link voltage control loop due to the inherent slow nature of capacitor voltage. Both of the inner and outer control loop are achieved by using the PI controller. B1Z is equals to R plus JX, P plus JQ, PC plus JQC, PLL ABC by DQ, PIWLC ESC modulation. So stated in the current Q axis became perfect constant synchronous vector with cross coupling terms of WL IQ and WL ID. Hence, feed forward is utilized to compensate the cross coupling effects and providing an independent current control. The PI regulators with gain parameters KP and TI are utilized to regulate the resulted D and Q independent current components. Then the PI regulators output signals are introduced to the PWM converter, which have a time delay T alpha defined by 1 by 2 FSW and caused by VSC switches based on the inner current controller has an open loop transfer function 1 plus TI S by TIS by 1 plus TA into S to 1 by R into 1 by 1 plus TS. Here we can see the diagram. So here we can see the diagram. We can in the equation GC into OL is equals to KP into 1 plus TI into S by TI dot S. into 1 by 1 plus TAS into 1 by R into 1 plus TAS. In the equation we can see current is inflowing in from the summing point E error 1 kp into K1 plus TIS by TIS. Thank you so much.